Bueno, acá lo tenemos ya, está en la sala, está pendiente, arranca el día 2 del MMS con esta conferencia, una de las más esperadas de todas. Estamos acá justamente con un invitado especial, Vedant Misra, que acá lo voy a sumar para que se suma. Hello, Vedant, how are you?
Hello, hola. Puedo hablar un poco español también, pero porque el material es un poco complicado, voy a hablar en inglés.
Ok, ok. Bueno, ya saben, tenemos acá. Así que si después le quieren hacer alguna consulta, quieren arrobarlo, quieren preguntarle, está en Twitter, está activo en Twitter, así que también lo pueden seguir por ahí. Así que nada, utilicen, recuerden el hashtag del día de hoy que es gomms.com. First, I wanted to ask you something, Vedant. Like, what are you going to talk about during this whole presentation?
So I'm going to be covering a few things. I'll talk a little bit about how machine learning works, and then about how machine learning has been applied to demand generation. And then I'll cover some of the recent advances in AI research and talk about how they might affect the future of demand generation.
Okay, I don't know if you have some, this kind of information, but this event on 2020, we had 65,000 people from all Latin America watching you. So during this year, we had the same objective, and there are people that are still registering to this event. So what I'm telling you is that this is going to be like a huge amount of mentions that you're going to be having in Twitter. And the thing is that we need this to be like for dummies and as well for people that are in like an advanced level. So we are going to be paying attention to a lot of what you're saying. We're going to be taking notes here. So I hope you're prepared later for some questions that people are going to ask using this hashtag GoEMMS. So now we're ready. Are you?
I think I'm ready.
Great. So I'm going to be back here in the backstage, and later I'm going to come back for the questions, right?
Awesome. Sounds good.
Listo, gente. Entonces arrancamos. Yo me quedo por acá y comenzamos con la presentación de Vedant.
Hello, my name is Vedant Misra. Thank you for coming to this talk. Today I'll be talking about AI and the future of demand generation. First, a brief overview of this talk. So I'll start by giving you a quick crash course on machine learning. There's going to be no math and lots of pictures, and this will let us establish some shared terminology and hopefully give you some understanding of the basic ideas in the field. Next, I'll discuss how machine learning has been applied to developing products for demand generation, in particular in sales and marketing. And I'll do this by describing some of the technologies and products that I've worked on in the past. After this, I'll discuss some more recent results, which focus on pushing the limits of large models trained on big data sets. And I'll cover some more recent work at OpenAI and Google. And after that, I'll cover some of the newest advances in AI, including models that can understand and generate images and video, and models that can use tools and take actions on a computer. And then finally, I'll discuss how these developments are going to come together and how this is going to shape the future of demand generation. So to start, I'll say a few words about my background. I studied physics and math with a focus on theoretical cosmology at Columbia. I was drawn to trying to understand things using mathematical models, but I wanted to apply those models to what I thought was an especially interesting object of study, which is people and society. And this was around the time that it was starting to become feasible to train machine learning models that could understand and generate language. Understanding language really felt like the fast track to developing machine learning systems that really understand people. So I started a company called Kenvi, where we were focused on generating personalized language for marketing automation. Kenvi was eventually acquired by HubSpot, and then I worked at HubSpot for some time leading the machine learning labs team focused on developing new products with deep learning. While I was at HubSpot, it was becoming clear that there was something magical that happens when you train very large models. And OpenAI was a pioneer in this field. So I moved to OpenAI to work with large models. And here I was managing the reasoning and algorithms teams. And the problem I was focused on was trying to develop machine learning systems that can perform reasoning heavy tasks like solving math problems or writing computer code. And now I work on research at Google, still focused on solving reasoning problems and on pushing the limits of large models. And at Google, I worked on systems like Palm and Minerva, and I'll say a bit more about these later in the talk. But first, let's establish some shared terminology. And we'll start with a quick crash course in machine learning. And there will be no math, I promise. So the first question is, what is a model? You can think of a model, sometimes talked about as an AI, as if it's a machine with an input funnel and an output funnel like we show here. And it's a complex machine full of lots of components. But the way that it works in its essence is that we pass it inputs and it makes predictions. Inputs go in, predictions come out. Inside this machine are a large number of tiny gears, each of which we can turn. And they're all arranged in a very particular pattern. Let's say each gear can have a value from -1 to 1, and we can dial the value of that gear. Each of these gears represents a parameter in our machine learning system, such as a single weight in a neural network. The process of training a model is that we set this machine up and we set the gears to random locations to start. And we give this model an input and it makes a prediction. But that prediction is likely to be bad. In fact, it's likely to be garbage because at the start, the positions of the gears are random. So the output is completely random as well. And we don't like these predictions. It's only when these gears are tuned to very specific positions that the machine can make correct predictions. So what we do to achieve this is that we train the model. This is equivalent to tweaking each of the gears so that the output becomes gradually less incorrect. Now, if we did this by hand, it would take forever. In a modern neural network, there can be billions of these gears or parameters, and tuning them each by hand is impossible. So this is where the learning comes in. We train this model so that the gears turn on their own bit by bit. And this is the expensive part. It costs money to train a model because the computer has to do a lot of work. Well, what work does it do? Well, the computer uses this model to make a prediction. Then it checks the answer by comparing it to the true answer, and it computes an error. And then it tweaks all of the gears just slightly to make the error a little bit lower. And it repeats this step millions of times. The end result is that you have all of the gears set to the best possible positions given the configuration you originally set up, and the predictions made by this model look more and more like the ground truth predictions that you would like over the course of training. And this is what we were hoping for. Now you can give it inputs and receive useful predictions. And this is a model that we can deploy in production or for various applications. So that explains neural network training. What about neural network architectures? You may have heard terms like transformer or LSTM or autoencoder. Well, these are all terms for different ways of arranging these gears. Every architecture is just a particular way of arranging the gears. And here we have one particular way of arranging what happens to be 48 gears. We see there's a small grid and then there's a big grid. But in this other configuration, this other architecture, we have a different setup for these gears. This configuration of the parameters is a different architecture, but both architectures have the same number of parameters. Both architectures are the same size. Something else that we can do is change the number of parameters in our network without changing the architecture. So here on the left, we have the original version of our network, and on the right, we have the parameters arranged the same way, but we've scaled up the number of parameters. There's simply many, many more parameters. So the way we refer to this is that we've scaled up the model. Another way to scale is to increase the size of our data sets rather than the number of parameters in our model. In this case, we keep the number of parameters the same, but we feed in a larger amount of data when we perform our training, indicated here with these wide arrows and larger inputs and predictions. Another very important thing to understand is the objective. In other words, what is it that we're trying to get this model to learn? This is determined largely, but not entirely, by the data that we use. So here's a few different kinds of objectives that we could train on. For example, our input could be an image with an output being the image caption, or it could be a piece of text with the output being a continuation of that text, or it could be a frame of a video with the output being the next frame of the video. And we can construct objectives like this for any task that we find interesting. Great. So now we understand some of the basics of machine learning and have some shared terminology. Next, let's jump back to the timeline and I'll describe some common and conventional applications of machine learning to demand generation. So this is starting with work that we were doing at ChemV. The problem we ended up focused on at ChemV was accelerating the day of someone working in sales and marketing. And we wanted to do it with machine learning. So if you work in sales and marketing, your job is to get people to buy your stuff. There's bits and pieces of information all over the internet about people, companies, and products. If you're a good sales rep, you can use that information to get people's attention and predict things about who might be interested in what you're offering and why. So here we see a piece of news about someone named Ryan Levine joining some company named Blipper, and we see that he wrote a blog post about being a product manager. This is all information that you might want if you are reaching out to Ryan. Here's another piece of news about this company. They've started a partnership with ADP. Again, useful information if you're evaluating this lead or reaching out to a prospect in general. So to harvest this data, we built a distributed pipeline for information extraction that scraped a variety of sources of data. We then structured that information, and we used that output to train models for personalizing sales and marketing content. So the result was that you could send personalized messages at large scale to your recipients. These use a standard template with machine-generated snippets. So what you're seeing here, underlined in blue, are customized snippets of language generated for this recipient. And our goal was to try to make it possible to send timely messages to targeted accounts with customized messaging. Here's an example of one of our prototypes. On the left, we can see a set of criteria that specify the user we're going after in this email campaign. And on the right, we see a templated email, but it contains these magic template tags that have content that is populated by a machine learning model in a way that is personalized to each prospect. So this is what we were working on at ChemV. ChemV was acquired by HubSpot. I then spent a few years working at HubSpot to lead the machine learning labs team, working at the overlap of research, engineering, and product. And we worked on a variety of machine learning systems focused on sales and marketing. And these are all examples of demand generation products in which machine learning is useful. So one central problem in demand generation is lead scoring. The core problem here is to figure out who is going to buy what and when are they going to buy it. One way to model this is as an inference task in which we predict the probability that a contact is going to be associated with a closed deal within some window of time. And the goal of training a model like this is that it's intended to help sales reps prioritize their leads and help marketers evaluate marketing efforts early into the campaign. Now, this is a hard and central problem. It's very important to business. It's difficult to predict market dynamics in a heterogeneous environment with limited information, but the ultimate goal is to come up with a score for each prospect, as we show here, based on the likelihood that they're going to close a deal. Another problem we worked on was content strategy. The core problem here is, what should you write about? What are your readers and potential buyers interested in? How do you get your material to stand out and attract attention? So what we did is that we modeled this as an inference task. We compute the probability that a given phrase is a core topic, and we compute the probability that a given phrase is related to a topic. And the goal here is to help marketers figure out what to write about so that they can get traffic. The technologies that we used here did include some deep learning systems, such as Universal Sentence Encoder, but also conventional topic models, such as probabilistic graph models like LDA. Another problem we worked on is bounce protection. No, not this kind of bounce protection. We're talking about email deliverability. So this is a core problem in marketing. There are bad actors, spammers, and fraudsters who send emails that bounce. And what we want to do is detect bad actors that are damaging the reputation of the IP addresses that we use to send our emails. And so we model this as an inference task where we predict the probability that any given list is going to be flagged as a bad list by various spam trap services. And the goal of this is to reduce bad email sends and generally improve email deliverability, as well as the reputation of the IPs that are used to send these emails out. Another application is send time optimization. So here we compute the probability that a contact will open an email if the email is sent at a certain time. And in principle, the optimal time to send an email is the time at which that probability is highest. So we compute this for various windows, and we recommend that we send the email at the time when that probability is highest. Another application we were working on was messaging products. So HubSpot has bots and messaging baked in, and this is a very powerful data set and a very powerful mode of interaction. The data is powerful because it's typically humans talking to humans about what they need. And it's a powerful mode of interaction because this feels a little bit like a universal interface. It feels like you could do anything through chat if it just worked well enough. Now, this was an early prototype, and things have come a lot farther since then in the direction of building powerful conversational systems, which I'll talk about soon. Another great source of information is calling data. So we've talked about emails and deals and chat, but of course, another big part of the workflow for someone in sales and marketing is talking on the phone. There's a lot of interesting work happening in call analytics, and there's a lot of valuable information in call transcripts. In theory, the truth of every deal is in the transcript of the call, or perhaps in the audio recording. One can tell if the buyer is engaged or if they're instead likely to push a deal out or just drop out of the funnel. So we launched transcriptions in the HubSpot product, and this gave us a very rich stream of information. And we worked on a lot of stuff here around information extraction and summarization of these call transcripts. Finally, Smart Compose. So we brought text auto-completion to HubSpot using the same kind of technology that powers Smart Compose in Gmail and Google products. Now, text generation has also come a very long way since then, and I'll talk about that next. Okay, so that's how machine learning has been applied to demand generation in the past. To understand how things are going to change in the future, we have to talk about the big story in AI in the past decade, which is scaling. So this is a graph in which each dot is a machine learning model or a machine learning system. The x-axis is the date that that model was developed or announced. And on the y-axis is the amount of computation that was used to train that system. Note that the y-axis is log scale, and every grid line here is a jump of 100x. So every grid line is 100 times increase in the amount of compute that was used. In that window from 1950 to 2020, we've seen a 100x increase in compute usage 10 times. So in total, an increase of roughly 1,000 trillion times in compute usage. This is absolutely insane. And to conceptualize this more clearly, here's that same plot, but on a linear scale on the y-axis instead of a log scale. What you can see is that there's been an exponential explosion in the amount of computation that's being used to produce these systems. In the upper right here are Minerva and Palm, both systems that I worked on, which used colossal amounts of computation on the order of several exaflops. And I'll share more about these later in the talk. Next, let me zoom into the last 10 years of this plot. So here's the last 10 years of this plot on a log scale again. And here we're showing only headline results. So this chart includes language models and NLP systems, including Word2Vec, GPT, GPT-2, and GPT-3, as well as Palm and Chinchilla. It also includes game-playing systems such as AlphaGo and MuZero, which play Go and chess, and Libratus, which plays poker. Also shown here are image models, including Inception V1 and DALL-E, which I will talk about later as well. No matter which domain we're looking at, with each passing year, more and more computation is poured into building these systems, and it results in increasingly impressive outcomes, and this has no signs of slowing down. A headline result of the past few years in this field is that the more compute you use, the stronger your model becomes at downstream tasks. So here's a plot from the GPT-3 paper. These are training curves for the GPT models. The y-axis is error. Now, if you recall from the schematic about machine learning training, the training process computes an error and then updates the weights by turning the gears to reduce the error. So here we see over the course of training, the error goes down. The x-axis is time as we train the model. The purple models at the start are small models, and the yellow models are big models. And the bigger you get, the lower their error is, which is to say the farther down on this graph they go. This is a different graph from Google with different models. These are Google's Lambda models. Here, we don't see the full course of training for each model. We just see where the curve ends up after some fixed duration of training. But again, the darker dots here are smaller models. The lighter dots are larger models. And what we see is that more parameters means lower error. So in other words, if we scale the model size and we scale the dataset size without changing the architecture, we keep getting lower and lower error. This is what we're seeing here. The model on the left is a small model trained on small data sets. And on the right, we've simply scaled up the architecture and we're training it on a larger data set. And the result is that we can just keep pushing this and keep getting lower and lower error on the tasks that we care about. Now, this is a major discovery, and nobody knows what the limits are to continuing to scale these models. And nobody knows what the best approach is to scaling itself. And these are all active areas of study. Okay, so scaling models is a very important trend, and we have no idea what might be possible if we just build bigger and more powerful systems. And this is a lesson that OpenAI learned before many other labs. And one place we can see this is with GPT, GPT-2, and GPT-3. So the GPT series of models are trained to predict the next word in a large corpus of general web text. So for example, if the data sample we're training our model on is a recipe from the internet, we might feed it these words here. Let's write down the recipe for an apple pie. We start by preheating blank. Then we ask it to predict the output, to fill in the blank. And the correct output is shown here, preheating the oven to 400 degrees. Now, GPT had a few hundred million parameters. GPT-2 had 1.5 billion parameters, and GPT-3 had 175 billion parameters. And just by increasing the number of parameters in the network and the amount of data that we train on, we can get astonishing results. Scaling up to that size made it possible for the model to generate coherent long-form text in a way that had never been seen before. GPT-3 can produce natural-sounding text that some people consider indistinguishable from human writing. And as you can imagine, there are countless applications for a model of this kind. So here I've asked to say something nice about content marketing professionals, and it happily obliges, producing various reasonable snippets of text that are in fact nice things to say about content marketing professionals. And it can generate tweets, it can write poetry, it can summarize emails, it can answer trivia questions, it can translate languages, and it even writes computer programs. So inspired by this, we built Codex, which can write high-quality computer code. The approach for doing this, again, was to scale the model up to a large size, again, 175 billion parameters, and to train on a large data set of computer code. So here, it's still predicting the missing words, but the missing words are specifically code data rather than general internet data. So the input here is comment symbol, compute the length of this list, and the output that we would expect is return length of the list. And here's what you end up with. It's a model that can actually write code pretty well. So what you see here is Codex deployed inside GitHub Copilot, and it's coming up with ideas for comments. And then based on the comment, it's coming up with ideas for the code that should be written to address those comments. This is a simple example, and Codex is capable of much more impressive things as well. So these are some examples of scaling from OpenAI. Next, I'll share some examples from Google where we've had further results from scaling. So one system that benefits from scaling that we worked on is the PaLM models. So PaLM has 540 billion parameters. This is 3 times bigger than GPT-3, and it's trained on general web data, just like GPT. And this model ends up with several new capabilities that were previously unseen and are quite remarkable. So for example, it's pretty good at explaining jokes. So let me read this out. So did you see that Google just hired an eloquent whale for their TPU team? It showed them how to communicate between 2 different pods, and that's our prompt. And the model output is, TPUs are a type of computer chip that Google uses for deep learning. A pod is a group of TPUs. A pod is also a group of whales. The joke is that the whale is able to communicate between two groups of whales, but the speaker is pretending that the whale is able to communicate between two groups of TPUs. Now, I couldn't have explained this joke better than that. It's basically a perfect explanation. Clearly, this model has started to understand humor to some degree. It's also quite good at logical inference and at chaining together conclusions from multiple steps of reasoning. So here's another example. The input is Shelley's from Virginia, but is visiting that city with that famous market where they throw the fish. Going home next Tuesday. The question is it likely that Shelley will be near the Pacific Ocean this weekend? And so here's what the model says. The model says the city with the famous market where they throw the fish is Seattle, Washington. Seattle is on the Pacific Ocean. Shelley's visiting Seattle, so she will be near the Pacific Ocean this weekend. The answer is yes. It is likely that Shelley will be near the Pacific Ocean this weekend. So here we see the model can perform complex logical inference over several steps. This is difficult reasoning that involves retrieval of world knowledge and also common sense, and Palm excels at these kinds of things. Another system we built is based on Palm and is called Minerva. So Minerva is just like Palm, except we trained it on mathematical data. And this turns out to be enough for the model to learn to solve hard math problems. As an example, we might feed it the input, write down the equation of a line with slope 4 and y-intercept 3. And as an output, we would expect the equation y equals 4x plus 3. But it can solve much harder problems than this. How hard? Well, it turns out it can solve Olympiad track problems for college-age students. So here's an example problem that we gave the model. Now, there's no way for me to talk about Minerva without showing a little bit of math, so I hope this doesn't scare anyone away, but we're not going to be digging deep into this math at all. So here's the question. A particle moves so that it is at the position 3 sine t over 4, 3 cosine t over 4 at time t. Find the speed of the particle measured in unit of distance per unit of time. This is a pre-calculus problem in which the position of a particle is provided as a function of a parameter t, and we are asked to compute its speed. And also shown here is the target solution. So this is the ground truth answer for this problem, and it's what we compare the model's output to when we check whether it's incorrect or correct. Now, I'll emphasize that the model never learns from this kind of data. It never sees this. It was never trained on any of these problems. It was only trained on general web data, mathematical web data, and it still learns how to solve these problems. So here's the model solution. The model correctly sets up the problem by saying it needs to take the derivative of a position vector to get the velocity vector. It then plugs everything in correctly and computes that derivative here, and it gets 3/4 cosine t over 4, comma, negative 3/4 sine t over 4. It then takes the norm of that vector by computing the square root of the sum of the squares of each of the components, and it performs all the symbolic manipulation necessary to do this. Then it uses the trigonometric identity to obtain a final numerical answer, which is 3/4. This is the correct answer. So this is a model that's ultimately just a blob of numbers, 540 billion little gears in a certain configuration set to the right values, and it ends up understanding math well enough to solve these problems. And these are kinds of problems that humans train for decades to learn how to solve. As another reference point for the difficulty of this dataset, there's a prediction network called Metaculus that aims to forecast the timing of technological advances by crowdsourcing estimates. The estimated probability that a machine learning algorithm might achieve 50% performance on this task before 2025 was consistently around only 40%. But we can see here the effect that we had on the Metaculus forecast. So this date indicated with the orange arrow is when we released our paper, and the probability spikes up to 1. So we achieved this milestone years before it was expected to happen. And this is happening across the field, where results are coming faster and in a more impressive way than anyone expected. Okay, great. So we've seen models that can write long-form content and computer programs and can write solutions to math and science problems. These are all super powerful text models. But there's also been tremendous progress in the past year or two in generative models of other modalities as well. And all of these systems are going to totally change the game. Recently, a major goal of AI has been creating multimodal systems, or systems that can learn concepts in multiple domains. One of the biggest breakthroughs was DALL-E. I already talked about GPT-3. Think of DALL-E as sort of like GPT-3, but for images. It was trained on hundreds of millions of image-text pairs scraped from the internet, and it learns how to associate images to the words that describe those images directly from that data set. So here you see the output of the text prompt, a pentagonal red lunchbox, a red lunchbox in the shape of a pentagon. So DALL-E successfully spits out lunchboxes. And as you can see, some images of the red lunchboxes are hexagons, even though the text requests pentagonal boxes. So we can see the model's understanding is somewhat limited, but it can combine concepts it has seen before to create new images that have never existed. DALL-E was succeeded by DALL-E 2, which came out this year. This is an approach that uses a completely different architecture and a larger data set. There's a famous painting by Gustav Klimt called The Kiss. Here we see DALL-E 2's rendition of alternate versions of this famous painting. This model clearly has a robust understanding of the visual world, including objects and their properties and how we describe them, as well as the visual styles of various artists. And it can be used to dramatically accelerate the creative process for any visual content. But images are just the beginning. So here's a short video generated by Meta AI's Make a Video tool. So this research builds on text-to-image generation technology to enable text-to-video generation. The system uses images with descriptions to learn what the world looks like and how it's described, and it also uses unlabeled videos to learn how the world moves. And so with this data, Make a Video lets you bring your imagination to life by creating unique videos with just a few words or lines of text. The example that you see here is for the prompt, a dog wearing a superhero outfit with a red cape flying through the sky, which is indeed what we're seeing here. Here's another one. So this is a teddy bear painting a portrait in surreal style. So you'll see the model understands what it means to have a teddy bear paint a teddy bear. But note that the hands of the painter teddy bear here do look distinctly human. They don't look like the paws of a teddy bear of a stuffed animal. Now, failure modes like these are common, but at this point are fairly minor. And so it's just a matter of time and scale before issues like this are resolved. Just as another data point for the benefit of scaling and how these issues might be resolved, here are samples from a Google model called Party, which is also text to image. So these are samples at 4 different scales of model: 350 million parameters, 750 million parameters, 3 billion parameters, and 20 billion parameters. The caption that was given to the model is indicated here. So it says, a portrait photo of a kangaroo wearing an orange hoodie and blue sunglasses standing on the grass in front of the Sydney Opera House, holding a sign on the chest that says, welcome friends. That's quite specific. What you can see is that as the model scales up, the quality just becomes dramatically better. At the smaller scales, the model has not learned how to produce coherent text, but at 20B scale, it definitely can. That sign says, welcome friends. At 3B scale, we can already see that it says something like welcome friend. It's not quite perfect, and it's holding 2 signs, but it's starting to get the idea of how to produce printed text. And then the orange hoodie and blue sunglasses are pretty consistent from small scale. You could say that at 250 million parameters, it doesn't even know what a kangaroo looks like. But as we can see, as we scale this system up by 20 billion parameters, it completely nails this problem and just becomes dramatically better. Okay, so we've discussed the problem of generating images. What about understanding images? As it turns out, this problem is close to being solved as well. So here's an interaction with a model called Flamingo from DeepMind. And this model can accept both text and images as input. So this is an image of a bowl. Inside the bowl is some sort of fabric toy, a monster made of wool or something like this. If you looked at it quickly, you might think that it's just a bowl of soup. So it's a very weird image. But the model has a perfectly reasonable conversation about it. We ask the model what's in this picture. It says it's a bowl of soup with a monster face on it. Then we ask, what's the monster made of? It says made of vegetables, and we correct it. We say it's made of fabric, and then it says, oh, okay, it's made of a woolen fabric. So this is a very human-like conversation. And we can see that the model can see and understand images, and it can even talk about them. Okay, so we have models that can understand images or generate images, but are there models that can do all of these things at the same time, that can generate text and also understand images and also maybe take actions in the real world? Well, DeepMind released a system called Gato, which does exactly this. It's a small network, but it can control a robot It can understand images, it can chat in natural language, and it can also play video games. So it can take actions and it can understand text and video inputs. So here's a schematic representation of the architecture of Gato. So here there are pink boxes that indicate observations and purple boxes indicating actions. So that means we can talk to this model and then sample from it, and it will generate a sequence of actions to take. So this is showing us the context for this model. Now, this unlocks an entirely new way of using these models. They transform from being just passive observers to actually agents in the real world that can do things. So the question is, what kinds of things could they do if they could perceive and also understand natural language? So this unlocks a very interesting new class of capabilities. So here's a short video from the startup Adept of their system Act 1. Act 1 is a transformer-based model that's trained on a data set of people completing actions on a computer. So what happens is that the model learns to take actions on a computer. The inputs here are in this orange box on the lower left. So it's things like log a call with James Veal. Earlier it said something like add Maxwell Nye as a new lead. And you see the actions that are generated by a model being automatically executed in this browser window. So it can add leads to Salesforce, it can add information to the lead entry, and all of this is just the tip of the iceberg. It can also do many other things, all of which involve navigating the web and interacting with applications from natural language instructions. Generally speaking, the goal of these kinds of systems is to get a model to be able to do anything you might do on a computer. Okay, now that we've covered the major advances in AI that it's important to be aware of, both from scaling text models as well as in the multimodal domain and also in modeling both observations and actions, let's talk about how they're going to affect the future of demand generation. Okay, so no matter what you sell, your buyer goes through these steps. First, they become aware of the existence of your offering, and we achieve this through advertising, inbound marketing, these sorts of things. Next, they have to have an interest in your offering, so you have to catch their attention. Then they enter a decision process in which they compare you to other offerings. And finally, they take an action to buy your product or to not buy your product. And of course, there are later stages of the funnel that involve retention and upselling and so on. And if you sell stuff on the internet, you likely have software that helps with each stage of this funnel. You might have MailChimp or HubSpot for email marketing, Salesforce for CRM, WordPress for blogging or SEO, Google Analytics for content optimization, and maybe a bunch of other solutions. And the reason you need all of this is because you are in competition with everyone else in your space for the limited attention of the same buyer pool. And you also have limited time in which to take action and make decisions. And there's an arms race happening for this attention, for this buyer attention. And the AI tools that we're developing are just going to accelerate this race. Here's an example of the arms race in effect from a few years ago, so we can see how technology speeds things up. This is a thread of emails I received some time ago, and everyone has many of these threads in their inboxes. It's become quite standard in the industry to use these tools that send a cadence of emails automatically if an email has not been replied to. And it's entirely automated. Now, this kind of technique worked for a while, but eventually you realize it's automated and the magic goes away a little bit. The value in a personalized email is the scarcity of the time of the sender. And as we automate cognitive processes, such as looking up information or figuring out what to say, there's no more scarcity. It's just machine time. And it starts to feel a little bit disingenuous. And this is an important way in which the landscape is going to change, and a way in which the perceived value of machine-generated content might go down. We're already seeing a proliferation of GPT-3-based content generation companies such as Jasper and Copy AI. These companies have systems for producing long-form content much more easily than writing by hand. And this kind of tech is taking the marketing world by storm. But ultimately, it's not unlikely that it could lead to a similar outcome to what we've seen in automation for email. People start to get tired of automatically generated content, and their bar for what constitutes quality content goes way up, just as the bar for what constitutes a quality cold email has gone way up. These days, when I write something, I ask myself, could GPT-3 have done this? Because if so, I probably need to add a little bit more information or nuance to what I'm saying. And I think this is exactly the kind of phenomenon that's going to affect these sorts of companies. There are a variety of companies now focused on making it easier to use natural language to perform tasks on a computer. So I just showed you a short video of a depth model, Act 1. OpenAI has a paper about a similar system called WebGPT, and the company Inflection AI has raised hundreds of millions of dollars to build language interfaces to computers. What this means is that in just a few years, we'll be able to have models use our software tools for us. They will click buttons, they will scroll around, read information, and queue up decisions for us to approve of or reject. In other words, the products that we use day to day, email, CRM, campaign management, etc., might all be used by a model instead. So now you say, okay, that sounds great. I would love to just put my feet up at my desk and relax. I can sit there and talk to my computer and it will add leads and do all of the work. By the way, in case you were wondering, that was a machine-generated image from DALL-E 2. Here are a few other versions I asked it to produce, and it just made them in a few seconds. And so if you put your feet up and you just talk to your computer, you might think, okay, it'll do all the grunt work of data entry and processing, but it's still going to be me that's making the key decisions and deciding what campaigns to run. But what I'm here to tell you is that even that may change. It may seem crazy to think that these models could one day do a good part of your job, including the part that requires high-level cognitive load. But there's a technique that people are using that might actually make that feasible. That technique is learning from human feedback. So in this approach, we train a second model, here the reward predictor, on human feedback. And we use this model to improve our base model. And the way that we combine this with a model that takes actions is that you could give it feedback on the actions that it produces and make its future action sequences more correct. So maybe in the beginning, the model makes some incorrect decisions when it uses your computer. Maybe you ask it, draft emails to my top prospects. And it does this, but it uses language that you wouldn't have used, or maybe it selects prospects you wouldn't have selected. But with some feedback, it learns how to do it correctly, which it can do with this reward model. Another way in which AI could change the landscape is if it starts to develop an understanding of the economic graph. So every transaction in the world happens in the context of a rich ecosystem of agents, which includes potential buyers, sellers, suppliers, influencers, and many other nodes. Now, building a map of all of this is very difficult and time-consuming, not to mention that within each organization are large numbers of people who need to be mapped out. It's difficult to model all of these relationships, but this is the information that tells you about the likelihood of someone buying something or needing something that you're selling. In a way, this is what lead scoring is all about, distilling all of this information down into a single number. But so far, the systems that have done this have been fairly limited and myopic. But with AI systems that are generally intelligent and aware of what's happening in the world, this may become much easier and much more powerful. Another transformation we can expect in the near future is that it'll become increasingly difficult to harvest and use data about individuals. There's been a wave of legislation in the past few years that empowers users to lock down their data and restrict its usage. And what this means is that the networks that already have a lot of user data, such as Google and Facebook, will both see their advantage grow, but also experience greater pressure to secure that information. And it also means that when we're trying to make predictions about individuals, we might need to rely a little bit more on machine learning to fill in the blanks about them, to try to guess things about them with less data. And as models become more generally capable, this is going to become an easier task for them. So to summarize, scaling compute and data is a very powerful recipe. This is the recipe that was used for GPT-2, GPT-3, Codex, Palm, Minerva, and many other major results, and we don't know how far it's going to take us. We're already seeing remarkable new capabilities emerging in these models, and in the next few years, the research community is going to push this even farther. We've also seen that generation and perception of images, video, and audio are becoming feasible, as well as to interface the perception of images and text with the generation of sequences of actions, which can then be executed on a computer or in the real world. And all of this is going to transform every aspect of the buyer and seller journey. So now you might think this is a little bit of a scary future. Computers doing work for us, understanding and generating everything we think of as uniquely human. Why are we doing this? Do we even want the world that this is pushing us toward? Well, I'll just end with a word about our motivation. So the motivation for many of us who work in this field is not at all to automate all humans, but instead to build the smartest possible computer, or in other words, to solve intelligence. So consider all the amazing things that humans have achieved with human intelligence. Our civilization, our science and art and technology is a testament to the power of intelligent agents cooperating with each other. But here's how we usually think of ourselves. We tend to think of ourselves as being much smarter than AI systems and simple animals, and we think that there's a wide spread between unintelligent humans and intelligent humans. But by and large, we think humans are at the top of the pack, smartest system that there could ever be. But what if the reality is not like this? What if it's more like this? It could be that there's not much of a gap at all between the smartest and least smart humans, and that AI could rapidly surpass us before we even know it. And the question is, what happens on the right side of this curve, on the right side of Einstein? We don't know. The hope is that if we have super intelligent computers, they could unlock all kinds of new futuristic technologies, such as advancements in medicine that improve or extend human lifespan, or new discoveries in physics that make it possible to develop sci-fi technologies like matter replicators and holodecks and faster than light travel. Thank you for your time. Now I'd like to open it up for questions.
Well, thank you very much, Vedant. Um, questions. I have like so many questions, things that I mean, I just found out since you showed us everything that could be possible actually using this kind of machine learning algorithms and stuff. So I think it's like there's a lot of questions. There's a lot of people that sharing with the hashtag GoEMMS. And I don't know. I think one of the first thing that I want to ask you is like, and you just said it, these could actually surpass human capability of dealing with things, like professionally and even, I don't know, and at home with things, right? So are we going to be like replaced for all this kind of stuff? I think that's something people is like asking on online in many ways.
Yeah, it's hard to predict exactly what's going to happen in the long term, but at this point, it seems fairly likely that we'll have some transformative AI system that can do a lot of economically valuable work within just a couple of decades, if not sooner. And it's not at all clear how society should manage this transition. The advice that I have for people who are thinking about what the world's going to look like soon is that it's quite important to, I think, remain abreast of these new advancements and to think about how the world is changing and what new technologies are emerging. And then also to start using these systems, because all of these technologies are ultimately being implemented by companies, and these companies want users. So the fundamental principles of how the economy works don't go anywhere, and it becomes of tremendous benefit to people who, independent of what they're working on, to use these kinds of tools and to learn how to accelerate their own work. It's also a good idea to keep thinking about what kinds of value we can deliver that machines cannot deliver yet, and to try to sort of remain conscious of things that are uniquely human about our interactions that we don't expect machines to be able to replicate in the near future.
Well, pretty much human nature, right? Our essence. There's a question that I just found out use with the hashtag. It's what advice do you have for people that work in this field to deal with the advances of artificial intelligence for marketing?
So I think certainly keeping an eye on these new products and services that are being developed with AI is a great idea. Learning how to use them and determining what their limitations are. Um, Now, one can only do this if one knows about them and is trying them out. So I think this is something that I strongly advocate for. And then remaining agile about the actual definition of your own role. In other words, if systems can do more and more of what you used to do, in principle, you can reshape your role so that with the time that these systems have freed up, you're doing things that they cannot do. Now, this isn't always easy. If you're stuck in a rut and you're always doing the same thing every day, and then a machine comes along that does the same thing, that's not going to be a good situation for you. But if you can instead adapt to this new world and add value on top of what the system can do, then you're in a very rarefied group of people who not only have the skills that you have in this field and the expertise and background, but also the ability to accelerate yourself by using these tools.
Great. So keep agile and try to find a way to adapt. That's pretty much it, right? There's another question that I have here. How long do you think it would take before we have transformative AI such as CGI for civilians, for dummies, I think, for us?
Hmm. Now, I think people's timelines about transformative AI or AGI seem to vary a lot. Some people think, well, 10 years ago, a lot of people think that it would never happen or that it wouldn't happen for hundreds of years. But now it's starting to feel like it's very likely to happen that we'll have machine learning models that can do a tremendous fraction of what an intelligent human could do. And the question is, how long is it going to take? And so, based on the way things are going, I mean, I have a shorter timeline than most people, and I think that it can happen in on the order of the next decade or two. But there's plenty of people who think that it's going to take longer than 30 years, maybe even 50 years. And these are very different worlds to plan for. If it's happening in the next decade, then we all need to adapt real quickly and uh, change the way that we work and think about what this new world is going to look like. But if it takes 30 or 40 years instead, I think we have some time before these systems permeate through our society and start changing the way that we live and work. Either way, a transformation is coming, and it can only help to be sort of on top of this change and aware of the things that are being developed.
I have a bunch of questions actually. I want to ask you like a lot of things now that we have you here. But I think there's something that I've been wanting to ask someone with your expertise and everything that you've done. And I think that one of the things, like, a lot of us are using it right now for certain tasks. We are using this kind of artificial intelligence like Jasper, like with copy, with posts that we do online, with emails. There's a lot of people using those. Is it I mean, what's your advice for using these kind of platforms that give you all this knowledge and all these solutions? But I mean, are they are they reliable? Is it something that we have to keep an eye on when we are using it? Do we have to check before we send it? I mean, I know there are some checklists that we suggest to people that use those, right? But what's your advice with these kind of platforms?
Yeah, great question. Because it really gets to the heart of the limitations of these language models, which I did not talk too much about in this talk. Um, and there are lots of limitations. So, one kind of limitation is that these models can sometimes produce harmful or undesirable outputs. And that's something that you certainly would not want to send in a mass email campaign to all your entire lead list. I think for in general for these products that are using large NLP systems such as Jasper, they I would imagine have ironed out a lot of these kinds of issues and make it's generally, I'm guessing, fairly hard to get harmful outputs from these models, especially if you're only focused on producing web style long form blog content. But there's other kinds of issues that can happen as well, in addition to being harmful. For example, the model can very easily just say things that are false. It can make up statistics or it can cite things that never happened. And there's, at the moment, no really good way to determine when a model is doing this. People are working on this. They call this the problem of hallucinations, where the model will just say something that's untrue. And I would expect in the next, several years that this is going to be a problem that a lot of people work on and mitigate with language models. But at the moment, it's still a big issue. So I think it still does make quite a lot of sense to, investigate the samples that the system is producing and confirm that they align with what is true and what is correct, as well as with the tone and sort of general timbre that you expect from your outbound. Um, that said, they're definitely a tremendous accelerator, right? I mean, you go from a world in which you just start with a blank Google Doc and have nothing to start with, to a world where you can produce, thousands of words that are not bad, that you can just proofread at this point. And so, tremendous power, but I think it needs to be these systems need to be used carefully, and their outputs do need to still be monitored.
So that's pretty much what you said before, that we human tend to actually get a better outcome if we actually put some part of us, right, and everything
Totally.
that these machines do. So I'm gonna have one last question, and it's gonna be some sort of a reflection or some advice that you would give to someone who has a startup, or who maybe has some project and they want to succeed, and actually, like, maybe they don't believe so much on it, but when you actually do something like you did, that you had your project and there, it was like so good that HubSpot bought it, for example, and you get to that. Maybe when you started, you didn't even think that you were gonna get that kind of attention. What would be your advice for someone who has a project, is working on it, and want to be successful on it?
Well, I mean, there are plenty of people who have talked about this and about the right way to run startups and to uh, be committed to a vision and deliver value through it and achieve product market fit and all these things. Um, there are some standard lessons that I think are important to live by if you're building a company. So one thing you mentioned is maybe this hypothetical person does not believe too much in what they're doing. So I'd say that's the first thing they should address. They should definitely believe in what they're doing and have some sort of deep-seated passion or excitement about the general direction that they're pushing in. Otherwise, it becomes quite difficult to keep working on a startup. And for us, that meant, for me in particular, that meant building systems that could understand and produce language. That was the core, sort of fundamentally exciting thing about these systems, rather than increasing someone's lift on their marketing campaign just slightly. Right? That's not the true vision of what we were trying to do. So I think having a vision that you're actually passionate about is quite important. And then when it comes to just sort of chugging along, I think having just faith in what you're doing and just sort of continuing to push and trying to show people the value in the way that you want to transform the world and how you think you're going to do it. I think that's quite important. Learning to communicate that vision and get people to see how you think things should be and how we can make that happen together. All I think quite important for getting people to see your vision and buy into it.
Well, great, great. I think that's great advice. And coming from you who have been through all these stages, I think it's really valuable. So thank you a lot for being part of this second day of the EMMS. I hope that you have a lot of mentions, and I hope that you also have a lot of work to do in answering all those questions, because that means that your content, your thoughts, all this experience really got far. So thank you again, in part, from all the Doppler team who organizes these EMMS years after years. So thank you for your time.
Thank you, Ennio. It was great talking with you, and thanks, Doppler, for organizing this event. It's been awesome.
Great. So, well, that was Vedant Misra. He taught us a lot about artificial intelligence from Google. And we're going to go back to Maria, who's waiting for us.